Alright, welcome back. This is probably our last video for PDEs. Well, actually, I'll do a quick little classification video of PDEs, and then I might look at the ambiguous solution for the wave equation, and I might also do what was I thinking of? Fourier transformations. But if I have time to do those, I'll do them. If not, then I won't. I'm definitely doing the classification though. That won't take long. So through this problem, we have a Laplace equation on a full circle again. This time, Neumann boundary conditions. I'm going to be basing this video a lot off of the first example we did of the full circle. So I highly recommend watch that video first, because I'm going to kind of skip through this one, because we know it's the same thing but with a Neumann boundary condition. But actually, hold on, it wants it on the inside of the circle. So that's one difference. But anyway, step one, we separate the variables. We were left with this ODE and this ODE. Actually, I'd also recommend to watch the last two examples before you do this one, because it'll make sense for you'll see why when I get to solving for R sub n with the bounds, because this is on the inside of the circle. First problem was a full circle, second problem was inside. So if you watch those two together, this problem should be pretty easy. So watch those two before this one, and then watch this one. So we separate the variables, we do our boundary value problem. This is the same exact thing as the first example that we did. When we have no defined boundaries anywhere. We have no end to our circle. We only really have an initial condition for the whole circle. So what we're going to do is we treat theta as having to be periodic around the circle. So we base our boundary off of that. So what we found from example 1, go back and watch it, that R sub n was C sub n R to the n plus C sub n, well, hold on. Why do I have that written there? That should be lambda sub n. Sorry. C to the n. Wait a minute. Okay, forget that. I don't know what I was doing there. We have 2. Remember, we have 2 for this one. Theta naught equals C naught. And we have, so that case, we also have this one here. Right, so that should be that for that. Let me make sure that's right, what I have here. I'm not sure what I did. I don't know why I have that written there. Okay. But step 3, solve for R. I'm going to copy this right here. All of this. This is the same thing as the last one, actually, because this wants the solution on inside of the region. So we make the same assumption as before. We want the solution on the inside of the region, so U must be bounded when R equals 0. We just know that, right? So if r equals 0, this term here, is undefined in that case, so we're left with this. So r sub n is equal to a sub n, r sub n. Excuse me. Step 4. Let's go ahead and just write out the general solution, right? So you know how to do the fundamental set of solutions. It's the same thing, just an extra step. So u of r theta is equal to, for this problem, remember we have an a naught term because of this. That's technically c naught here. Well, I'm gonna relabel them because of just standard convention. But that's the c naught term that we had. N equals 1 to infinity. I'm gonna rename this as a sub n. Remember, these all got multiplied. All these terms got multiplied when we did the fundamental set of solutions. R sub n sine of n theta. So that's our general solution. Now, this is a Neumann problem. So, which problem was it? I think it was the wave equation. We had a full Neumann problem. Yes. So, you'll see something weird is going to happen here, because remember we need to find u of r. Remember our condition was u of r of theta. U sub r of theta. That would be, let me see, can I write a sum? There we go. N, right? Pull that, and this is just like, what is it called? What we just did, right? With the Euler equation, n, or this is just like proposing a solution, then it's r to the n minus 1 times, I did them both in one shot, by the way, because you have this term and you have this term, because we have this one, which is just this, and then we also have cosine, which becomes sine. Oh wait, no, I made a mistake in my notes. We're taking it with respect to r, so we only have to differentiate this term right here. I made a mistake in my notes. This is the same thing. N b sub n r to the n minus 1 sine of n theta. So the extra terms in this one would be n and the r to the n minus 1. Well, first of all, let me actually do our initial condition. It's just f of theta. This would be n a sub n a to the n minus 1 cosine n theta plus n b sub n a to the n minus 1 sine of n theta. And our extra terms are the a sub n minus 1 and the n. These are the extra terms. This is what we're going to divide by. Now you notice, our a sub naught is gone. So as you can see, we can see a sub naught went to 0 for the Neumann condition. So it is required that Remember, a sub naught, that term is always going to be integral 0 to 2 pi. This is for the circle. G of theta d theta is equal to 0 is necessary. Right? It tells us that that is this. That's what taking the derivative of that tells us. So by that, we know a naught is 0. We know a sub n. We divide by the extra terms. Right, pi is just the length, half a period, right? Notice how I'm integrating over the full period, so that's why I'm not multiplying it by 2. Times cosine n theta d theta. B sub n, this is going to be the same integral. G of theta, is it G of theta or F? Oh, it's F of theta. I knew, okay, F of theta, sorry. Is it F of theta? Hold on. No, it is G of theta. I used two different things in my notes. It's G of theta. Where did I use F? Here. Whoops. It's G of theta. For this problem. Times sine of n pi and theta d theta. Yeah, so there's our solution. So I'm going to go ahead and copy this. And there's a solution. So this would be the, hope that's right. Let me just double check that. Oh, a sub naught is 0. So we can just get rid of that term. Right. So there it is. There's a solution. This is the last video for full solution of PDEs. Like I said, I might do, well, I am doing classification of PDEs next. That'll be a quick little video. It's pretty simple to go over. Won't take long. That's a pretty simple concept. It just classifies what kind of PDE it is. Is it parabolic, hyperbolic, or I forget the other one. But that can help us with if you later go into, what's it called? I think it's method of characteristics. Instead of separating the variables, I think it's called method of characteristics. It's very important to be able to classify PDEs. I don't think I'm going to do method of characteristics, but I'll definitely do the classification, and I might do the Amberlert solution. That's not too bad for the wave equation. That's a really, that's actually a pretty simple way of solving the wave equation. And then there's also Laplace transformations, which I can also do. I might do that. But, hope you enjoyed the video. See you in the next one for classifications.